Good morning, everyone. Let me know.
Good morning, sir.
Thank you. We'll start with the second part of our cryptography. Last lecture, we discussed symmetric key, and today we'll look at asymmetric key, which is also known as public key distribution or public and private key. And the main algorithm that is being used in this asymmetric key distribution is called RSA algorithm, named by the first letter of the authors or inventors of the work, which is US, Samir, and Elderman. So let us look at the basic concept, understand it, and I would suggest you to spend time, experiment. And when I give a third assignment, there'll be some questions based on using this RSA. So primarily in symmetric key, both sender and receiver have the same key. And we have a challenge, how do they share? But assuming they're able to share the secret key some way outside the channel, and then they use it to encrypt and decrypt. In public key cryptography, sender and receiver have different keys. And that means with different sender receiver, you can have different key pairs. And that's how the public key encryption basically works. When I say key is public, so when you look at the keys, asymmetric keys, key has two parts. One is called public and one is private. Public key by nature, public means it is known to everybody. Private key means it is known only to the sender or the receiver depending upon who is using it. So private key is known only to a person, whereas public key is known to everybody in the world. And depending on whether private key is by sender or receiver depends on the context and what application context the key is being used. And we'll look at those aspects in a while. So let's consider how does it work, and then we'll look at some examples. Most of the material are taken from the textbook 1, even though your syllabus says textbook 2, but textbook 2 has very minimal minor description, and textbook 1 has given you detail, so it can help you understand, and then for writing you can use what was given in textbook 2. So assuming Alice needs to send a message to Bob, and Alice has a message, a plain text message, M. Alice needs to send this message securely so that nobody in the intermediary, they can see the message but can't decipher it, can't get any meaning out of it. So she needs to encrypt the message. She uses the encryption algorithm and uses Bob's public key. Because she is sending a message to Bob, I just want to make sure that nobody is able to tamper and corrupt the message. So message integrity is maintained, message confidentiality is maintained, not the authentication part in this approach. She uses Bob's public key. Using public key, that's called KB1. Using the algorithm public key KB1, she encrypts and get the ciphertext applying KB1 to message M. And then this ciphertext or encrypted message goes to Bob. Bob has to use decryption algorithm applied on the ciphertext. Bob will use his private key called KB2. Using this KB2, using the ciphertext message C, which is KB1 of M, applies KB2 on it. And when he applies that, he gets plain text out, which is derived by applying KB2 decryption algorithm on KB1, and which is the encrypted message, and then you get message back, that plain text back. And this is the primary concept of public key cryptography. So what are the key main requirements for using this public and private key? First one is that we need to have two key pairs, KB1 and KB2, even though in this lecture we are using KB1 as public, KB2 is private. You can interchangeably use one as a public. There is no such thing that only first one should be public, other private. Any pair of keys that meet the requirement, one should be public, another should be private. And the key should be such that encrypt using one key, decrypt using other, and that gives the message. It could be other way out as well, KB1 outside and KB2 inside, that will still work out. Second part is, given one key, let's say KB1 is public, that means KB1 is known to everybody in the world. Given this public key KB1, it should be impossible or computationally infeasible to determine the private key KB2. Because if somebody can determine, then security is broken. So two key requirements for asymmetric key or public key encryption is the key should be such that encrypt using one key, you get a ciphertext, then decrypt using second key, and you get the original plain text back. Second requirement is, given one key, which is known to everybody, it should be computationally infeasible to derive second key. We are saying computationally infeasible because in theory, given sufficient time and high computing power, using brute force, one can always determine. But if given sufficient time, which could be millions of years, so if we can decrypt the key after millions of years, that is pretty much useless because messages today decrypting after a million years has no meaning, but in theory it can be done. So it should be computationally infeasible, or we can say practically impossible to figure out second key given the first key, and these are the main requirements of a public key. And this is what is used in RSA algorithm, which stands for reverse Samir and Adelsam. And by the first letter of their author's name, the algorithm is known as RSA algorithm. Before we look at how the keys work, the whole thing depends upon modulo arithmetic. Like modulo is basically remainder. So let's review a few things which we'll use. We know that if we take numbers a modulo n plus b modulo n, which is same as a plus b modulo n. If we take a modulo n plus b modulo n mod n is equal to a plus b modulo n. Similarly for minus a modulo n minus b modulo n on modulo n gives you a minus b modulo n. It is applicable to multiplication as well, or division a modulo n into b modulo n gives you, and take modulo n further, because multiplication can give you a larger number, do the modulo again, and you get a star. And once we know this, from this we can figure out that a modulo n to power d is same as a power d modulo n y, because I can say a modulo n power d is equal to a modulo n into a modulo n into a modulo n d times, and that basically means, and by this a modulo n star b modulo n, which is same as a star b, so a modulo n multiply a modulo n d times, I'll basically give a power d modulo n. And that is how the modular arithmetic works, and this modular arithmetic is being used to work with our public and private key. Let's verify with a few examples. Consider two numbers. Let's say x is equal to 14, n is equal to d 10, and d is equal to t. So let's look at x mod n power d modulo n, which is 14 modulo 10 power 2 modulo n. So modulo 10 power 2, 14 modulo 10 is 4, which basically gives you, sorry, it basically gives you 4. That means 4 square modulo 10, which is 16. 16 modulo 10 is 6. This is what we get. Same way, if you were to do x power d mod n, x power d square, which is 196. 196 modulo 10 again gives you 6. And hence, the two numbers are correct. So we basically use this a modulo n power d is same as a power d modulo n, and this property is extensively used in RSA algorithm to work with public and private key. Why does this algorithm work? Because you're looking at pure mathematics, and we say our messages are text. But when you look at the number representation, let's say hello, all letters we represent in ASCII. ASCII at the end of the day, we write in numbers. So each message is nothing but a bit pattern. And bit pattern can be treated as number. And when you treat the bit pattern as number, once you have a number, we can apply the modulo arithmetic, and hence the algorithm would really work. So when we say encrypting a message, all that means is computing mathematically on the powers and modulos and working on it and then finding encryption, and same is true for decryption. So encrypting a message basically means encrypting a number by applying modular arithmetic, and vice versa even for the decryption part. So take an example. Consider that message m is equal to 01100001 in hex. This value is hex 61, which corresponds to alphabet small a. When you're writing a, let's say, message ABC, actually message will be represented in binary as 61, 62, 63 in decimal, or we can look at the whole number in integer, get respective number. So for the letter A, the decimal number equivalent is 97, and now that we have actual number, we can always apply the modulo arithmetic. That is what we do in the encryption part. And same way we will do the decryption part. So what is involved in creating these keys? And that is where the crux of the algorithm lies. So primarily algorithm says two large prime numbers. And large prime numbers means numbers should be at least 1024 bits and even larger. Because when we say given a public key, it should be computationally infeasible to drive the other key. That can only happen when the numbers are large. For a small case, computers can do the job quickly. Hence, the number has to be large. So choose two large prime numbers, and let's say these two prime numbers are P and Q. Given these two large prime numbers, compute two integers called n and z. N is equal to P into Q, and z is equal to P minus 1, Q minus 1. So again, choose any two prime numbers, let's say P and Q. Then choose, after choosing this P and Q, compute n, which is same as P star Q, compute z, which is same as P minus 1 into Q minus 1. Having done that, now choose a number E. Choose a number E such that this number E is relatively prime to Z. When we say relatively prime to Z, that basically meaning that n is not a prime number. Z is not a prime number because Z is a multiplication, n is a multiplication. So neither n nor Z is a prime number. But you're saying choose E less than n such that E is relatively prime to Z. So relatively prime to Z means E has no common factor. For example, if I were to take number 24, Number 24, 5 is relatively prime, 7 is relatively prime, 11 is relatively prime to 24, and even 15 is relative, no, not 15 because 3 is a common factor. And that's the way it works. And let's say if my Z happens to be, let's say 49, Z is 49. Now, relatively prime 49 is not a prime number, but 3, 5, 15, 24, these are all relatively prime to 49 because there is no common factor. So all we are saying is, having computed Z, find one number E which is less than n, which is relatively prime to Z. Having found a number E or identified number E, compute a second number D such that ED mod Z is equal to 1. Or we can say ED E star D minus 1 is divisible by Z. And when you find these two numbers E and D, these basically become your public key and private key. We can say E comma n because n is known. The E comma n is a public key and D comma n is a private key, or we can say D comma n is a public key and E comma n is a private key. And having done that, we have public and private key. So one of the key could be known, and given one public key E comma n, it should be computationally infeasible to determine D comma n. And this can only work when P and Q are very large numbers, more than 1024 bits. If they are less size, then they could be computed and security could be completely broken. Now we look at how does the key really work, how do we use that. Now that we have the key, we have a key E and we have a key D. Let's say given a message M, message M could be text, string, anything, but at the end, since they are representing in bits, it becomes a number. So given the message M, which is a number, so even a text would be interpreted as a number because of ASCII representation. So given the text message M, we encrypt by computing M raised to power E modulo N. Now this is the computation, mathematical computation. M is a number, E is a number. We can certainly compute M raised to power E modulo N, and that gives the ciphertext C. So when a user needs to transmit, let's say user want to send a message M, user compute message C, which is M raised to power D modulo N. It computes this value assigned to C, and C becomes the ciphertext, and user sends this ciphertext to the other end. Ciphertext C would nothing but will appear as some number, but a hacker in between can't really figure out. When the receiver receives this message C, all that receiver does is, this C is again a number, receiver applies the formula C power D mod N, and whatever it receives, it again D power mod N, and when you do that, you will get the original message M back. And that is the beauty of this algorithm. So primarily, because of this magic happens, so we say M raised to power E mod N, whole power D mod N, gives me message M back, and that is how things really work out. I will not go into detailed proof, but give you very minor idea into how does that work. And if anyone is interested, we can go to separate whole mathematics called Euler function, tot function, and all that. That lays the foundation. But at the moment, we'll basically assume. Let's work out an example. Consider that two prime numbers are 5 and 7. Then what is the value of n and z? Anyone? We said n is p star q, z is p minus 1 into q minus 1. So what is the value of n and z?
Sir, NS 35.
Yes. And Z
24.
24. Precisely, N is 35, Z is 24. Now choose a number E which is relatively prime to Z. Z is 24. We choose 5. 5 is relatively prime to 24. Now your job is to find D such that E into D modulo Z gives me 1. Having chosen E, what should the value of D be so that E into D modulo 24 gives me 1? Anyone like to give? E is 5.
Sir, 5.
5 into 5, yes, that should be 5 as well. We can do that, or we can even do this 29 as well. So both are fine. That also would work. Yes, 5 also would work. Can you give another number which is relatively prime to 24? We chosen first number 5. What could be another number you choose which is relatively prime to 24? It can't be
7,
6.
sir.
7 would be one. 11 would be another. 13 would be another. 17, 19. You can choose any number you feel like. Let's choose 7. Then what should the D be? Anybody else? Given these values, if you choose E is equal to 7, what should the D be? Anybody else? Susan?
Yes, sir.
Yeah, what would the D be? Is question clear? We've chosen P and Q as 5 and 7. N is 35. That is 24. We choose a number 7, which is relatively prime to 24. Now we want to find a number D, such that 7 into D would be give me 1 modulo 24. If you take 7, 7
So
into
7.
7 is 49. 49 modulo 24 is 1, because 24 into 2 is 48. So D becomes 7, and you can work out any other number. So need not be only one number, it could be anything. Now let us look at how does the entire encryption part really work. So we'll take a message. Let's say our message happens to be value 12 in binary. Now value 12. So what we want to do to encrypt? M raised to power E, which is 12 raised to power 5. When you do 12 raised to power 5, you will get the answer 24832, and this you have to do modulo n. Understand, when you're computing E and D, we do modulo Z, but when we encrypt, it is modulo n. So that's the property you need to look at. 24832 modulo 35 would basically give me 70. So my given message M, I computed, encrypted using public key E, 12 raised to power 5, modulo n gives me 70. To decrypt, I need to do C power D. Now D is 29, or I could do d power 4 as well, which could be 5. So 17 power 29, you can also do 5, that also would work. You get a large number, and when you do modulo n, you'll get back the value 12 again. And that is how the algorithm would work. So I would say you take some other number. Let's say my message happens to be 3. When a message happens to be value 3, using this key, this happens to be same. So in general, E and D would not be the same. You have to work with that. Let's say if I were to choose E as 11, my public key is 11. What should my D be? Consider that my E is 11. What would the value D be? Any thoughts? Work out something so that you help understand how things work. P is 5, Q is 7, let's say E is 11. What should the value D be? So that 11 into D mod 24 gives me 1.
So 11 itself.
11 itself?
Yes. 121 mod 24 is 1.
Yeah, 120 will give 121, so that should be fine. So in this case, it happened to be symmetric, but in real life, that would not. So take a number, apply the encoding, do the computation, and then you get the answers. So take any two prime numbers, find any E and Z, different alternatives, encrypt, do the modulo, and then you work out, you'll get the answers, and that you get the same message back. And that is the crux of my public private key algorithm, or what we call RSA algorithm. We started with 12, computed m raised to power e. We got the ciphertext 17, 17 power, I can 29 or 25, I'll still get the same answer, and that is what would happen. You can take any other number. So try this. Let's say work out with 7, spend 5 minutes, and see if you were to use same value 12, use this E and D, do you get the same answers? Spend few minutes, and then we review. So what would be 12 raised to power 17b? So it will be huge number, which is, if we to look at, it will be 35831,808, and when you divide by so you can use Excel or any calculator to figure out these values, and then say this is the way the RSA algorithm. Now, why does this mathematics work? I will not go into too details. If you want to go deep mathematics, we need to look at some other basic modular mathematics, but we'll make some basically axioms, and using that we'll show this how it works. It is known that for any two values x and y, x raised to power y mod n, not xy, it is x raised to power y mod n is same as x raised to power y mod z mod n. So whether I write x raised to power y or x raised to power y mod z, I'll get the same answer as long as n is equal to p into q and z is equal to p minus 1, q minus 1. You can look at the mathematics part, but to this identity, and make you into the identity, we would show that our encryption actually works. Now, we need to show that C power D mod n is equal to M. And what is M? What is C? M raised to power E. So C power D mod n, C is M raised to power E mod n, whole power D mod n. Now M power E mod n is nothing but M power ED mod n, because M power E, M power E, M power E D times, which will give me M power ED mod n. Now using the formula M power ED mod n is same as M power ED mod Z mod n. Now we know that we have chosen the number E and D such that ED mod Z gives me 1. So this gives me M power 1 mod n, and which basically gives me M mod n, and M is less than n, so we get value M. And that's the way this mathematics works. So we basically get, when we encrypt M raised to power E, we further do any computation. So it's all mathematical computations in the RSA algorithm, and that's how the algorithm basically works. The beauty of this RSA algorithm is whether we do M power E first or M power D first, we basically get the same answer. For example, in this case, whether I used to do M power E first, whether say C is M power E or C is M power D, I can do M power D and then do E. I'll at the end get M power ED. And because of this reason, I can use any keys as a public and second key as a private. And this property basically means you first encrypt using one key, decrypt using other, or vice versa, encrypt using other key, decrypt using first one, you'll get the same message. So there's no hard thing that first number has to be public and second has to be private. Essentially, all we are saying is whether we use public key followed by private key, or we use private key followed by public key, we basically get the same answer. So depending on context, whom we are sending, we basically do that. And we deal with authentication tomorrow, and tomorrow next lectures, we look at if I need to authenticate somebody, so receiver want to authenticate sender, so sender would use his private key to encrypt, and private key is known only to the sender, and receiver can decrypt using public key, so message is authenticated. If I want to send a message confidentially to receiver, I would use public key of the receiver to encrypt, send to the receiver, and receiver could decrypt using the private key that's known only to receiver. And depending on the context, whether to use public key as for encrypt or private key for encrypt, you have to make a decision based on what application context you are using. But in either case, after both encryption and decryption, receiver gets the original message which was transmitted by the sender. We already seen that why this is the case, because first case is M power E power D, which gives me M power ED mod n, which is M power D E mod n, power D whole power E mod n, which is basically the first case. So where does the security of RSA come from? If we were to choose the number E and D very small, anybody could do brute force and find the public key. So security comes from given public knowledge of N and E. How hard to determine D? And that basically means you need to find factors of N. Remember, when you choose the number P and Q, they're very large numbers, more than 1024 bits. So when you multiply the value prime number, N would be 2048 bits, and finding the factors of N without knowing the two factors P and Q is a really hard problem, even with today's superpower computing. It may take millions of years when we choose large numbers, and that's the reason when keys are chosen, they are chosen So if computer become faster, rather than using P and Q 1024 bits, you use the keyword number size 2048 bits and make it computationally much harder. And that's the reason you see increasingly when we started with DES, keys are just 56 bits, and today we use 2048 bits and even 4096 bits, because larger the key size, it becomes extremely difficult, computationally infeasible to find factors of n, because finding a factor is a very hard problem. It will take a huge amount of time, and that is the reason RSA gives you security. So how does RSA get used in the communications? You basically look at because we are using computation using two keys, doing mathematical computations, computing powers, and that takes a lot of time. So RSA is at least 100 times, depending on with the same key size, is 100 times more computing intensive than the DS, or you can say DS is at least 100 times faster than RSA, and when we use the public key, it basically becomes tough. So that means if you were to actually encrypt message, actual message using RSA algorithm, it is going to take too much compute power. And daily communication, we don't want to spend too much compute power. So typically RSA algorithm is not used to compute messages. However, what it used for a digital signature or kind of session key. When you use HTTPS, that means sender and receiver should be able to use shared single key. The RSA algorithm is used. RSA algorithm is used to determine a single shared key. So use some mechanism which is what we study next, which is Diffie-Hellman key exchange. So using a Diffie-Hellman key exchange that makes use of public and private key mechanism. So one-time computation you do and compute a session key. And once you compute a session key, which is symmetric key, and this key is used by both sender and the receiver. The beauty of that algorithm is that even the entire communication happens in public, no intermediary could determine what this session key would be. So primary use of RSA algorithm lies in determining session key and digital signatures. So like HTTPS, IPN, SSL, when you look at any of the VPN setup, RS is being used to do one-time computation to determine session key and use that session key to encrypt decrypt message. Once your session is over, you establish the next session, you do one-time exchange of second the next session key, use that, and since you are using different session keys for different sessions, so no hacker could actually figure out what is being computed, because by brute force, it will take millions of years or more to do decrypt these keys, and that means practically infeasible. And that is where the RSA or the public algorithm works. So to summarize, what we studied is we looked at the public key mechanism, the two keys, and these keys are derived using RSA algorithm with a mathematical proof, and use of RSA algorithm is to determine, identify a session key, and that means then we use symmetric key. Why use symmetric key to actual data exchange? Because data is huge, and using symmetric key is much faster to encrypt than using asymmetric key. So if you were to encrypt actual data using RSA algorithm, it will take too much computational time, and that is not practically feasible. So RSA algorithm is used to determine a shared key, which we call session key, and then this shared key is used to encrypt the entire message, because that becomes much faster. So normally the algorithm is very useful to agree upon shared key. Otherwise, user have to have separate meaning, and you can't decide on the fly what a session key is. And that is how the RSA algorithm works. So tomorrow lecture we look at Diffie-Hellman algorithm, which basically says how making use of this public-private key mechanism, the two end users can agree upon shared key, even though the entire exchange between sender and receiver is visible to public, but despite the entire exchange being visible to public, still nobody can determine what a shared key is, and that's the beauty of Diffie-Hellman algorithm, and that we'll study tomorrow. So I would say, as a practice, pick up some two prime numbers, compute n, compute z, find e which is relative to z, treat as a public key, find d such that ed mod z is equal to 1, that becomes private key, then take any message as a mathematical number, compute the power, compute the modulo, and then find the answer back and verify that the algorithm works. And that is what the magic is. So this brings to the end of today's lecture. If any questions, please let me know. Otherwise, you can drop out. Thank you. If no question,